Hello everyone, my name is Justin Plato and this is Group 11 and we will be speaking about randomized algorithms and its applications. Our group members are Kaylee Chang, Bumi Adeyemo, and myself. So this is just a brief overview of what we'll be covering, just a brief history of randomized algorithms, an introduction, the explanation of what they are, advantages and disadvantages, deterministic algorithms, classification between the two of them, the Monte Carlo application examples, and real-world examples. So a brief history was actually in the 1970s where Michael O. Robin created the closest pair problem, which helped improve the study of randomized algorithms. Before then, they weren't really that popularized, they weren't really that studied, and he really helped push it along to show that it's actually something that's worth taking a look at. As with this one, the closest pair problem that we'll go over in a little bit, it actually helped out a lot, specifically with being able to have more people study them formally and improve the algorithms over time. And it's mainly used within cryptography and mathematics. And the reason being with cryptography is because it's encryption. And with encryption, you're using randomized algorithms so that way you can go ahead and get the best encryption that you possibly can. Mathematics, of course, it's completely different. It's using proofs to help better other algorithms, and you're always going to get something different. So what are randomized algorithms? Randomized algorithms are used where a problem that is stated has some properties of it being random and has an input that is also generated at random. So basically, if you have a problem that says, let's go ahead and take a random input and go ahead and sort the algorithm itself and then produce the algorithm. So a quicksort function, you would go ahead and generate the random numbers, and then from there you would go ahead and sort the algorithm. However it's sorting it could take random points or random pivots, random sections of it, sort it, and then put it back out into an output. You're expecting an output no matter what. And this includes, like I said, rand within the program and also using random shuffle or even hashing. Hashing is something that takes advantage of this using such as the Robin-Karp algorithm, which another group actually covered not too long ago. And hashing is something very important within randomized algorithms. And like I said, during the process of it, it will take different paths, even though it has done it previously. So through each iteration, it takes different paths, but you're always expecting the same output or a close approximation to the output that you're getting throughout each iteration. So the advantages, you're testing a vast amount of cases using the rand function, and by being able to just test different inputs each time. And by taking advantage of this, we're able to test for sample cases that we would not normally think of. And so let's say if we have 50 different test cases, we know that we would get a solution from one of these for at least 49 out of 50 of these cases. Let's say one of them is not optimal. Well, 49 of them are optimal, and they each grow, or they each lessen each time case. And so we can go ahead and trace back to see what is the best case for each of them. And not only that, but we're using the rand or rand shuffle function of these methods. So in these methods, we're constantly using the rand function to generate random numbers or rand shuffle to randomly shuffle arrays, randomly shuffle different things that we may be testing. Let's say if we're trying to find a hidden string for a prefix of it, then we can go ahead and random shuffle each time, let's say 5 characters, and then be able to test and ask for inputs on these. It could always be potentially faster than what we would anticipate for it. Let's say if we have a different algorithm, that we may have completed, and we're thinking, well, this is the fastest we can get, but you implement a randomized algorithm, and it creates something faster, then you know that you're not done. You can always go back to it and refer back to what happened. The disadvantages, though, is that it doesn't always find the optimal solution, even though we always get a good approximation of it. It will never always be the best. We can always improve it. Sometimes it gives us the wrong optimal solution of it, and sometimes it does, and that's a very rare one. It does happen, because if it does happen more often than not, you most likely implemented it incorrectly. And so that's why you need to go ahead and test each with your randomized algorithm. You need to create a bunch of test cases, test it, and see how well it does work. So another thing also is that it does everything slightly different. It doesn't do the exact same thing all the time. It takes different steps through each iteration to solve the problem. So let's say if you find the optimal solution for one of them, but then the next solution it doesn't take the optimal solution, it's because it took a different path, because it's flipping bits. It's doing 0 or 1. Do I do this path for 0 or do I do this path for 1? It depends on which one you're currently taking. And inside each iteration, it'll always do it differently. And another thing that we can have it test for success 50 times, but let's say there are many times that it does not produce the optimal solution. That is an exaggeration, of course. It's the worst case scenario. So let's say you do 50 times, but none of them are optimal. Then most likely the algorithm was implemented incorrectly, or the it's just not optimal to even solve it, and it could just be a bad question in general. So that's basically randomized algorithms in a nutshell. They're pretty simple to understand, and it's really not that hard. So some things to think about. And what scenarios would you want to use a randomized algorithm? Can you think of any right now? If you can, go ahead and think about them for a couple seconds. If not, go ahead and we'll go ahead and go into the next portion of it. So we have the prefix string. This is a question that I got from Erico, great YouTuber, great person. He does competitive programming, and this is actually a competitive programming question. So it's basically finding the prefix of a string. So let's say we're given a string of S, and we're trying to find a hidden string within it, and we're given with the characters BMOPL. Each time you can ask if one of the characters is a prefix of X using a query. So let's say we have 200,000 characters. So that'll be our n, less than or equal to n. And the number of queries you can ask is 500,000. How would you solve this? You can go ahead and pause the video if you want. If not, I'll go ahead and explain everything, how it works. So we can do the naive solution. Basically, what we do is we ask each time if a character is a prefix of it. So is B a prefix of this, let's say we have 1, 2, 3, 4, 5. And let's say, is B a prefix of it? No. Okay, let's go on to the next one. M. M is a prefix of it. Now we go into the next one. M. Is O now a prefix of it? No. Is B? Okay. But of course this takes forever. We have to ask it 5 times, and it's a brute force, so that's why we get 5 times n, which is not good, because if you're doing it 5 times n for each one, you're going to run out of queries very quickly, because it just stacks up and stacks up. So how do we fix this? We can do a random shuffle for each character after asking each character for the prefix of S. So let's say we're given the first 5 right here. So the first one, we can just go ahead and start with BMOPL, and we can ask, well, is B a part of it? No. Okay. Then we go ahead and cross that off, and then we go to M. M is now right here. Is M a part of it? Yes. So we go ahead and place M, and then for the second one now, instead what we do is we random shuffle this entire string right here that we're given, and then we go ahead and ask inside the order it was shuffled in. So instead we can get P. Is P a part of it? No. Is L now a part of it? No. We go to the next one. O is, and then we continue doing it for the rest of these steps right here. So we're constantly shuffling these and asking each of these right here. But when we do this, we're asking it, we're getting 1, 2, 3, 4, 5 times. So we're asking each specific query for this, which then gives us 15 total for up here, divided by 5, because 5 different characters that we're asking for is equal to 3 times n, which is not that optimal. You can go ahead and see a solution already. I already have it down here, but if you guys want to work out how I got the solution, go ahead and pause it really quick. If not, I'll just explain it really quick. So for this one specifically, all you gotta do is just go ahead and instead of asking for the 5th character, you just tell it what it is. Because let's say if you exhausted BMOP, you already know that it's going to be L. So instead of asking the query, is this L? You could say, well, we already know what it is because P is not it, O is not it, M is not it, and B is not it. So we can just say, well, this is clearly going to be the answer for it. So that's why we can actually ask 1, 2, plus 2, plus 3, plus 4, plus 4, because you're getting 4 queries out of each of them instead. So you would get 14 divided by 5, which is about 2.8 times 10, which is good enough. That's basically what we're looking for right now, just good enough. We're not looking for the most optimal solution. We're just looking for something that's good enough or better than 3 times n, because then we won't run out of queries, and if we do run out of queries, it usually means that the solution is not there, because the interpreter or the interpreter could be malicious, but we're using the best case scenario, so it won't be malicious. So credit to Erico for this. Great YouTuber, great competitive programmer. He does a lot more stuff on his YouTube channel. If you guys want to ask him inside the discussion board, I'm more than happy to go ahead and provide that link for you guys so you guys can check him out more. And then also the closest pair problem. So the closest pair problem, as I discussed earlier, was solved by Michael O'Brien. Basically, you have these two pairs right here. So what you want to do is you want to grab the closest pair possible. So you go ahead, select a point, and then check by reference, by angle, however you want to do it, and see what's the closest pair that's possible in this grid. So you can check this one to this one, this one to this one, this one to this one, however you want to do it. But no matter what, these two are always going to be closest. So you can do it brute force way by picking a specific point onto the grid. And if you pick this one the first time, congrats, you solved it. But that's just one time. Let's say if the brute force method ended up picking from right here to right here to right here to right here, you're going to take up too much time to be able to solve it. So that's where randomized algorithms come in handy, because you can go ahead and select a random point and then from there try to find the closest nearest neighbor. So you go ahead and say, well, let's go ahead and pick this one. So randomly you select this one, and then from there you check, well, different angles and see which one is the closest. So this one would be closest to this one, and that would be determined by the angle that you would be able to calculate from it. And from there, you would go ahead and test this, let's say 100 times. So you would have 100 different points, each one generated randomly, and if you get this exact same board, you would get at least this one right here, this specific one, you would get it out of random, and then you would of course check the nearest neighbors that it has, this one, this one, this one, and this one. And once you do, you would find that these right here are the correct ones. And that's basically all that the closest pair algorithm is. You're basically taking two different points, and then from there you go ahead and just find out which this nearest neighbor is. So if you do the brute force method, for a randomized algorithm, if it's the worst case scenario, this goes inside n squared. This is worst case scenario though. It's never going to be this. Usually it'll be approached inside n log n, which is the most optimal that you can get for any algorithm. So with that, I'll go ahead and hand it over to Boomi, and she will explain randomized algorithms versus deterministic algorithms.
Hello everyone. Let's start with this short video comparing the two.
It's actually a wide open discussion whether randomization is actually helpful, because with considerable analysis, many randomized algorithms can actually be turned into deterministic algorithms by using a process called de-randomization. And de-randomization usually keeps fundamental properties such as polynomial running time or the base of the exponent. Randomized algorithms therefore might be a bit faster, but it's unclear whether this is due to luck, if you will, or lack of thinking. So if you were to pit these two against each other, randomization versus determinism, it's not really clear who would win or if it's a draw. So to conclude our exploration of randomization, what might be some reasons that randomization is actually at least a bit more powerful than determinism? Is it that randomized algorithms are in some way harder to trick into a worst case behavior as compared to determinism? And after all, we're analyzing all of our algorithms using worst case analysis. Is it that randomized algorithm can usually be easier to analyze than deterministic algorithms? Or is...
So the answer is the first two. The strengths of randomization include they can be harder to trick into worst case behavior and that they can be easier to analyze. So to give a little background on both deterministic algorithms and randomized algorithms, deterministic algorithms are algorithms whose behavior can always be predicted. Every time there is a certain input, the algorithm will react the same way with the same computational steps that will return the same output. So the algorithm is completely determined by inputs. Since the outcome is known and consistent on every execution, the runtime is polynomial time. Randomized algorithms, on the other hand, have behavior that can vary even on fixed input. They work great for when there is a significant uncertainty of inputs, and they generally can be used to solve any problem with a probabilistic interpretation. Continuing comparing, deterministic algorithms are generally easier to create than truly randomized algorithms. And algorithms that use random numbers may be considered deterministic if the random numbers come from a pseudo-random number generator. Randomization is best used in problems where deterministic approaches are difficult or impossible, and randomized algorithms tend to run faster. And for many problems, a randomized algorithm is the simplest, the fastest, or both. It can be easier to calculate the probability of error, and as you can see from the picture on the left, deterministic algorithms take the input and return a certain output for that input always. For randomized algorithms, in addition to the input, the algorithm takes a source of random numbers into it and makes random choices during the execution that will determine the output. So now I'm going to pass it on to Kaylee to talk about the categories of Las Vegas and Monte Carlo.
So randomized algorithms are classified in two categories, the Las Vegas pattern and the Monte Carlo pattern. So let's just go through Las Vegas algorithms first. So Las Vegas algorithms are only probably efficient, but is certainly correct. So this means that it gambles with resources that it consumes, like time and space, and uses a randomness aspect to guide decisions that impact the efficiency of the algorithm, but not its correctness. So what this means is that their output is always correct. But in terms of efficiency, like their time complexity and space complexity, it may vary or depend on the algorithm itself, which is what this part means, defined probabilistically. So their efficiency will, again, depend or vary depending on the algorithm itself. And Monte Carlo algorithm, so Monte Carlo algorithms are certainly efficient, but only probably correct. So it gambles with the correctness of its output, and its output may be incorrect with some probability. So what this means is that their efficiency, like their time complexity, will be better than compared to other algorithms. But in terms of their output, in terms of correctness, it might not be the most optimal solution, but I think in most cases, Monte Carlo algorithms will have one of the most optimal solutions. So the running time is deterministic. So the main difference between Las Vegas and Monte Carlo algorithms again is that Las Vegas, their efficiency will vary or depend probabilistically, and their output is always correct. And then Monte Carlo is the opposite, where their efficiency is certainly better compared to other algorithms, but their output may be incorrect or might not be the most optimal. So more about Las Vegas algorithms. Some algorithms that are considered Las Vegas algorithms are randomized quicksort and randomized graph and pathfinding algorithms. So just like a little review. So randomized quicksort or just quicksort in general. It's similar to merge sort, where it uses the divide and conquer method to partition the list of inputs. So it sorts a list of inputs using a randomly picked element as the pivot. And for randomized graph and pathfinding algorithms, some graph algorithms that you might know about are Prim's algorithm for minimum spanning tree and depth first search. So we'll go into more detail about these two algorithms and how the randomness aspect will make it better. So let's just go through randomized quicksort first. So I'm going to explain randomized quicksort in terms of deterministic and randomized method. So for the deterministic quicksort, it sorts a list of inputs using a pivot. And this pivot is usually the first element or the last element in the list. So the reason why we use the pivot as the first element or the last element in the list is because we won't know the actual set of inputs from to choose from as the pivot. So we would just use the first element or last element as the starting point of the whole sorting process. So we would compare each input in the list with a pivot to arrange the list into two partitions: numbers less than the pivot and numbers greater than the pivot. So we would keep on repeating this process recursively until all the numbers are sorted. So eventually, for deterministic quicksort, the time complexity will be, for worst case, O(n) squared, and best case, O(n) log n. So the reason for these two time complexities, for worst case, it will be n squared because it can be difficult to find a good pivot, since again, we don't know the whole set of inputs to choose from. So it's hard to determine whether it will sort elements efficiently based on that particular element that is chosen. So like the first or last element, we're not sure it will be like the optimal pivot to choose from, since it will, depending on the element chosen, it can take longer or more time in terms of iterations depending on that pivot. So rather looking for an optimal pivot, we would choose a randomly picked pivot, which randomized quicksort will come into play. So randomized quicksort, it has similar steps from deterministic quicksort. So you still need to choose a pivot, but the only difference is that the pivot is randomly picked. So randomized quicksort, it will always outperform merge sort. Like even though they use the same method in terms of like divide and conquer, it'll partition the list of inputs. Randomized quicksort will always be faster just because it uses the randomness concept or aspect. So the time complexity will be O(n) log n. So here's like some pseudocode to just visualize the difference between deterministic and randomized quicksort. So on the left is the deterministic quicksort pseudocode or algorithm, and on the right is the randomized quicksort. So you can see that they both look the same, and they use the same concept in terms of like sorting the list. But you can see that the only difference is that in deterministic quicksort, the pivot will be the first element in the list, and for randomized, the pivot will be randomly picked. So I'm gonna show just like a step-by-step example of how randomized quicksort will work. So here we have just like a simple example of how randomized quicksort will work. So first of all, let's just go through this pseudocode that was shown. So since it's just a simple example, I'll just use this. So I just wrote the pseudocode that was shown here. And as you can see, yeah, so we picked the pivot randomly out of the list, and we made 3 different lists. So one for storing numbers less than the pivot, one for storing numbers equal than the pivot, and one that for storing numbers greater than the pivot. So we will loop through the list comparing the numbers inside the list to the pivot and just storing them accordingly. And we will do it recursively until the whole list will get sorted. So if I run it, it'll sort this inputted list 2, 1, 5, 4, 3 accordingly. So let's just go into more depth about how this pseudocode or algorithm works. So Yeah, so we have like a list of inputs. So it's just a list 2, 1, 5, 4, 3, and we want to sort this list. So first of all, for randomized quicksort, we would pick the pivot randomly. So let's just choose 1 randomly from the list as the pivot. So it'll loop through the list, comparing each number to the pivot and sorting each number accordingly from, like, again, less than the pivot, equal than the pivot, or greater than the pivot. So we will compare the first element in the list first. So 2. So 2 compared to 1, it'll be greater, so it'll go into the greater than list. And then 1, it'll go into, so yeah, usually the pivots chosen will go into the equals than list. So the pivot 1 will go into the equals than the equals than list, and then 5, since it's greater, will go into greater than, 4 greater than, 3 greater than. So eventually you'll have 2 lists. So just the equals to list, which is only the pivot 1, and greater than list. We'll have 2, 5, 4, 3. So since we have 2 lists now, we would do it recursively to sort each of the lists. So there's no inputs in less than, so we don't need to worry about that. And greater than will need to get sorted still. So we would do this, we'll sort this list recursively, and then return the equals than value, since it's only 1 value. So it'll return the number 1 first, which is shown down here. So we will sort this list now, the greater than list. So out of these 4 numbers, it'll choose another random pivot. So let's just go with 4, for example, as the random pivot. So 4 will be chosen as the pivot, and again, it will compare each value and sort it accordingly from the less than list, equal than list, and greater than list. So 2 compared to 4, it will be stored into the less than list, which is shown here. And 5 will be greater than, will be stored here, and 4 will be in the equals than list, and 3 less than list. So there will be 3 different lists now. So 2, 3 for less than, equal than 4, and greater than 5. So since we're doing it recursively, it'll put together the less than list, equal than list, and greater than list together. But we're doing it recursively, so we're gonna do this less than list recursively first to get it sorted. So we're gonna go through this set of numbers first. So the less than list here will only have 2 and 3. So again, we'll choose a randomly picked pivot. So let's just go with 3 as the randomly picked pivot. So it'll compare the 2 numbers again and sort it into the list accordingly again. So 2 will be less than 3, so it'll go into the less than list, and 3 will go into equals than here. So once this is done, it'll only have 2 and 3 in the new set of iteration list. So it'll put it together again, so that it'll recursively do less than list again. So less than list, it only has the number 2 so far. So from the pseudocode before, when there's only one number inside the list, or one element in the list, you'll just return the element. So it'll just return 2 at the end of this iteration. So right now in the new sorted list, or in the process of it, it'll only have 1 and 2 so far. So it'll return 1 and 2, but it'll also return this equal than number here, since that's in the same iteration. So you'll return 1, 2, and 3. And then after that, it'll go back to this previous iteration that we were doing with the equals than. So it'll return 1, 2, 3, and 4. And then later on, it'll go back to the greater than recursively list, which has only the element 5. So since 5 is the only element in the greater than list, you'll just return the number 5 after that. So the full sorted list will be 1, 2, 3, 4, and 5. So more about randomized graph and pathfinding algorithms. So most graph and pathfinding algorithms, they can use the randomization method to increase its efficiency and improve its time complexity. So usually for graph and pathfinding algorithms, they're mostly used for random maze generations. So for example, Prim's algorithm, it'll find a minimum spanning tree for a weighted undirected graph and builds a tree or path one vertex at a time where the total weight of all the edges is minimized. So how it works with random maze generation is that it picks a random wall from the list and creates a passage if the block or node divided by the wall is unvisited. And it'll mark, as it goes on, it'll mark its neighboring blocks, walls, and add them to a list. And it will repeat this process until all the neighboring blocks or nodes are eventually visited, which will create the whole maze randomly. So I'm going to show you a video of how this randomized Prim's algorithm will generate this maze.
So before we actually get into the code of this maze, I first want to go over how this algorithm works. So the first thing it does is it creates a 2D array, and all the cells in the array are blocked, which means like they have these like walls. And then it picks a random block wherever on the array, it's highlighted in blue, and then it goes to all of the neighboring blocks around it and joins them together, like so. And it just repeats this over and over and over again until all of these red tiles, which are the neighboring blocks, are gone. So it'll do this for the whole maze, and then once it's done, it'll stop. And usually this sort of maze algorithm is used with walls, like each cell has 4 walls, but the one that I used, each cell is either a wall or a passage. Walls obviously are these walls, passages have no walls in them. And then what the algorithm checks for is it picks a random one of these red tiles and checks to see where a tile that is a passage is, and it'll just connect to that, and I'll delete the one in the middle. So like you can see over here, it just happened there. And it just repeats this until the whole maze is completed. And so now that we've gone over...
Oh yeah, so after that part, he just goes through the code.
So before we...
He just goes through the code, and it takes a while, so I'm just gonna skip through here to here, where he explains a little more, or visually shows how the maze will eventually turn out. So I'm gonna skip to here.
Run this again just to show you one more time. You can see it starts with this blue cell, and then it just spreads to all of the other red cells, and it connects them. And I don't know the exact specifics behind it, but when I'm making this maze, my criteria for it was that I wanted a lot of dead ends and like cuts, and it does exactly that. But you might notice one problem with this maze generation algorithm is the fact there is no definitive start and finish, because Prim's algorithm, the algorithm that I'm using, is actually used for like electrical engineering to find like the shortest path for like a wire to travel, but it's just randomized, so it just makes a cool looking maze, except the maze doesn't really have a start or a finish. But that works perfectly for me because this whole maze project is meant for a game that I'm working on. I might explain it in a future video, like in a devlog, where I don't really care about a start or finish. All I care about is like finding little alcoves and like putting little like treasure chests there, and the players will have to pick them up. But if you guys want me to elaborate on that game concept and show you videos through my progress through that game development, then make sure to comment down below.
Yeah, so he made this algorithm, he made this maze generation using randomized Prim's algorithm by choosing a random starting point, and then just randomly choosing walls to eventually fill passages with, and just checking if they're unvisited or visited, just to make the random maze. So each time this algorithm will run, it'll make a completely random and different maze.
So now we're talking about the Monte Carlo class of randomized algorithms. Quick reminder, as my teammate mentioned earlier, Monte Carlo algorithms are certainly efficient, but only probably correct. This means they produce the best solution or most efficient solution to a problem within a certain probability. So Monte Carlo is a class of randomized algorithms that use repeated random sampling to guess a solution. The more random points included in the sample, the more accurate the solution becomes. The more times the algorithm is run, the more accurate we can guess a solution. These algorithms are mainly used in three distinct problem classes: optimization, numerical integration, or for generating draws from probability distribution. I will be talking about three specific examples. There's Karger's minimum cut algorithm, the traveling salesman problem, and the Rabin-Karp string search algorithm. So to understand Karger's algorithm, we must discuss the minimum cut problem. The minimum cut problem appears in graph theory. It is when you're observing a graph that is both connected and undirected. Connected meaning there exists a path from any point in the graph to any other point in the graph. And undirected meaning we're not looking at a directed graph with incoming and outgoing edges for specific nodes. The question this problem aims to answer is, what is the minimum number of edges that can be cut or removed from this graph or network to make this network disconnected? A cut is a partition of the vertices into two non-empty disjoint sets. This can be used to see how vulnerable a network is or how robust it is. As you can see from this picture here, we have more edges concentrated on both the left and the right side. And if we were to cut these two lines straight down, we would have two separate graphs. The original idea on how to solve this problem before Karger's was called the max flow min cut algorithm. It was deterministic and it was shown to be slower than Karger's. There are many applications for this, including determining the strength of a system if failure of any of the components were to occur, strength of a vehicle or motorized transport network if a road or multiple roads get blocked off, and so on. Karger's algorithm was developed by David Karger in 1993. It is a randomized algorithm for finding global minimum cuts. The runtime will be bounded by a fixed time function determined by the size of the input, so i.e. a worst case runtime bound, but the algorithm may return a wrong answer within a small probability, as we mentioned happens in Monte Carlo algorithms. The main idea of this is to iteratively contract randomly chosen edges. Okay, so now observing how the algorithm works, the input would be an undirected graph and the output would be the number of minimum cuts or the edges of the minimum cuts found. So we'll start off by randomly selecting an edge of the graph. So if we were to use this example here on the right, that would be, we could randomly search and we can get 3 and 4 possibly. So step 2, we'll contract the nodes, which means to collapse the edge between the two nodes. So 3 and 4 would now be merged into one supernode, carrying along all the connections between the subset nodes. And any self loops that would be created in this transition would be ignored. So now 3 and 4 are one node. So following step 3, we would now iteratively repeat until there are only 2 nodes or supernodes left. So if we randomly search and select an edge again, and we get this edge between 1 and the supernode of 3 and 4, we could contract those nodes and merge it into one supernode, as seen here. And then if we go again and we get the edge between 2 and the supernode of 1, 3, and 4, we can contract those, and then we would get this graph here on the right. And now we only have 2 nodes and slash supernodes left. If we cut the 2 edges between node 5 and nodes 1, 2, and 3, 4, here, we will have a disconnected graph. And we can see that 5 would be separated. So if we were to come here and see this in the beginning example, where we have 1, 2, 3, 4, we can see from this that if we cut the edge between those two, there's 2 edges between them, those correlate to these 2 edges, the edges between 5 and all the other nodes, and we would get a disconnected graph. So now this video shows what I just did in animation form with the nodes identified as letters instead of numbers. So starting from the first step of randomly selecting an edge, we would pick this green edge here, which is between B and D, which was our 3 and 4. We would merge those 2 nodes into one supernode. And then we would search again, going through the whole random process, and we get the edge between letters A and D, the purple edge, that correlates to our 1 and 3, 4. We merge those 2 nodes together, and then we get the one supernode that we had up here. So then we go again and we get this edge again here, merge that, and now we're here. So as mentioned before, we cannot guarantee the solution. This algorithm states that a minimum cut can be found with a high probability. So if you look at this second example below, down here, if we went in a different order, we could have ended up with 3 edges as the last result. And it's true if you come back to this first graph and you could cut the edges between 1 and 2, 3, 4, 5. That would be these 3 edges, 1, 2, and 3. It would make a disconnected graph. But that is not the minimum number of cuts that we need to create a disconnected graph as seen here. So this is considered unsuccessful when a lower number of minimum edges could have been found. Now let's look at some actual code. This is all written in C++. So the main part of the function that really does the algorithm is this while loop here. We're going to repeatedly loop until we only have 2 vertices left. So we're going to start off by picking that random edge, and then we're going to find the vertices or the endpoints of the current edge. If they belong to the same subset, we won't consider the edge, or if they don't, we would union them, and then we subtract the number of vertices and continue looping until we only have 2 left. Once we only have those 2 left in that last step, we would count the edges between the 2 components and return the count. That's all this is doing here. So lastly, we would run this code a bunch of times, and the lowest number of minimum cuts that appears the most is the value it'll return. So like with the previous example, it might run the first time and get 2, which is the correct answer as minimum cut value. It might run again and get 3, but it's most likely to get 2 the more times it runs. This makes sense because if you think about it, when you're picking edges randomly, it's more likely to come from parts of the graph that contain the most edges. So now we're going to talk about the traveling salesman problem that we've heard about here before. So let's do a quick refresher first.
What we have here is a puzzle version of the traveling salesman problem. So to play this, you have the path you're going to take. As a salesman, you can start at any town. Let's begin at York. And then you have to work your way around the board, imagining you're the salesman visiting as many cities as possible. Maybe you've got a boat. And at the end of this, you have to end up back at the city where you started. However, if you're not very efficient, you're gonna run out of length, right? It's actually possible, let me try again, to start at one of these cities, let's do Edinburgh this time, and visit every other city and end up back where you started. Oh, wait. Now, actually, to try and solve a problem like this, what I'm doing is really the only thing you can do. You can just try different methods. There are a few strategies you can use, like you trying to find the nearest city each time, but there's no mathematical solution. Mathematicians are still trying to find a solution that will give you the shortest possible path to link all of these cities together.
So as he mentioned in the video, the only thing you can really do for a traveling salesman problem, it would be randomization, because there's no mathematical solution to solving this. There are several applications, including solving vehicle routing problems, logistics planning, and scheduling. So here's another quick video that kind of just shows you how that randomization would kind of work. So for 8 cities, there'd be 5,040 different routes that can be taken. So we can start off with the greedy algorithm approach, where you just choose the closest one. And this is the output it would give you. It's suboptimal. So starting off with some randomization, and then swapping results is random with randomization. If we get better results, then we're going to continue. As you can see at the counter down in the left bottom corner, every time a new improvement is found by randomly swapping, you lower the distance. So as mentioned again with Monte Carlo algorithms, you may not get the best result each time. So there are techniques available to avoid this. Simulated annealing. So there are many approaches to solving this problem, including involving a randomized parallel approximation algorithm. The next algorithm we're going to talk about is the Rabin-Karp. So it's a string searching algorithm or pattern matching algorithm. It was developed by Richard M. Karp and Michael O. Rabin in 1987. The main idea here is to find the given target pattern by computing a rolling hash of the substrings from a given text. So as you can see here, we have the main text would be given here. Then we'd have a pattern that we're looking for, and we could use a rolling hash to compare the values. The original approach would be a brute force algorithm where you would compare letter by letter. But as you can probably imagine, that's very inefficient and would take forever. But if you had a rolling hash, you'd be comparing just the hash values at that point. So here's the example of if we had this as the main text and we repeatedly take substrings of the text as seen with this here, and then we hash that value and we would already have calculated the hash of the pattern since that's not changing. Then we can just compare the hashes and that would tell us if there's a match. So this assumes all probable matches are correct, guaranteeing a linear runtime, but with a small probability of false positives. Now let's look at some actual code for it. So this here is written in Java. This is the part of the function that really does the algorithm. So we're going to start off by getting the length of the text. The text is the full string that we're comparing the pattern to. Here was the rolling hash function. We're going to see if we're starting off with a match. Then we're going to loop through the entire length. These two lines, all they do is update the value of the hash. So as we're moving along the text, we would want to take away the contribution from that first. So if we're going from left to right, you would want to take away that first leading value. So that first leading character from the left. And then we would want to add the hash contribution to the hash from the most right that we're scooting to. The new updated character would be involved into that hash. So if there is a match, you would return. And this is all for the Monte Carlo version. As mentioned before, Las Vegas algorithms are only probably efficient, so not as efficient, but certainly correct. So in the Las Vegas version, you would check for a substring match, and if there is a hash match, you would continue searching until there's a false collision. If there's a false collision. Las Vegas here would be the equivalent to modifying the Monte Carlo version to call itself on the remaining portion of text if an equality check fails.
Alright, so now I'll go ahead and speak about the applications and uses of randomized algorithms. So we'll start with cryptography, which is encryption, random map generations within games, and searching algorithms, which have already been covered, but we'll cover more in depth as to what they're used in. So for encryption, we can go ahead and use the Enigma machine. So the Enigma machine, of course, was developed during World War II by Nazi Germany, and it was their way of encryption back then. So as you can see, it's a very complex system. Just by even looking at it, it's just a bunch of wires and it's a mess. But it was very sophisticated for its time, and how they cracked it was very interesting. I read a paper on it. It's very interesting how everything works. If you want to look more into it, go ahead and leave a comment on the discussion board. I'll be more than happy to link it for you guys. So let's go ahead and see how it all works. So with the Enigma machine in the previous image, you notice that there are many wires connections. Even right here, there's a lot of wire connections right here, if you can see them on the plug board. And that helps to encrypt the text even further than what it already is. So there are 26 letters, of course, but we have these right here. These are the rotors, and there's 3 interchangeable rotors. Each of those rotors right there, there's 5 of them in total that it comes with. So you have 5 options for one, 4 options for the other, 3 options for the other. So with 3 interchangeable rotors, we have 26 characters in each of them. And since 26 times 26 times 26, because each of those rotors you're able to pick from, you now have 17,576 different combinations just for the rotors themselves. So you're able to choose between that many characters to be able to encrypt this message. But that's not all. So since you're able to do that, you have the options of 5 times 4 times 3, like I said earlier. So we have to take that into account. So that's about 60 different arrangements just for the rotors themselves, because you have, let's say, this rotor to this rotor, this rotor to this rotor, just different combinations all around. So what you have is now you have 60 times 17,576 for the different combinations for just letters and rotors, which is about 1,054,560, which is a lot of combinations just by itself, which is ridiculous. But they wanted it even more encrypted. So there's a lot of fancy probability and things that I just can't be bothered to read. So here's the shortened version. Basically, you have 26 factorial divided by 6 factorial times 10 factorial times 2 to the power of 10, which equates to 150,738,274,937,250 different combinations. So that's just with everything so far, with all the letters, all the rotors, and the different arrangements for the rotors themselves. Now, the thing is that you have these different plug boards right here, like I said. So that's where also this probability comes in, because you have different types of plug boards, and you have each letter is connected to each one. So let's say A can be connected to V. So if A is connected to V via this plug board, let's say you press A right here. A is now clicked and you send a electric signal, and it goes through, routes it all the way to V. From V, what ends up happening is it sends another signal to the rotors, and it'll pick a random letter from this rotor. So let's say if it's at 1, it'll go to, like, say, a 2 or 26, doesn't matter. Then it goes to the next rotor. And this rotor right here, it'll go ahead and change the position of this rotor, and then it'll output it to the next rotor. And it'll change the position of this rotor, and then come out, back, change the position of this rotor, come back over here, change the position of this rotor, come back, and you see these lights right here. These lights are diodes, and this is another way to encrypt it even further. So once it passes through A to V to the rotor, 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 back, 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 it'll light up one of the diodes. And so when it lights up one of the diodes, let's say this right here is a better image, you can see that it has A right here. So when you click on A right here, then it'll light it up. But that's not all. What ends up happening next is that it'll go to E. So that'll be the final output of this Enigma machine. So once you get to that point, then you're finally done after you go through all this complicated stuff right here. So let's do this one more time. You go from, you have your plug board, you have 20 different combinations for it, A to V. So A to V to the rotor, to this rotor, changes it each time, back through the rotors to A, and then it goes to W. Or to E, whichever one. Doesn't really matter since this is an example. It's pretty crazy. Germans were definitely crazy back then. So when you look at it and you think, wow, this is really crazy, what does the final number actually come out to? So the final number actually comes out to this right here. So 60 times 1,054,560 times the 150,738,274,937, or 274 150 quadrillion, 738 trillion, 274 billion, 937,250, which equates to 158 quintillion, 962 quadrillion, 555 trillion, 217 billion, 826,360,000 different combinations. Now that is a horrible thing to encrypt, and the reason it works so well is because of how many combinations there are and how random it truly is, because you don't know which one it is unless you know which rotors they ended up using. And that's one of the ways that they were able to use it so efficiently, is that they had their own schematics to tell them how to input the rotors, so that way they can go ahead and send the messages and decrypt it themselves, because they know exactly what rotors that they used. So for this to being decrypted by other people is that basically amazing. I don't know how they did it. It was basically one of the portions of it that I read, it said that to decrypt it, there's a flaw in the system. So for it to go ahead and to use it properly, to decrypt it, we can go ahead and say, well, there are 6 characters that are not used within the codes itself, and that was a big factor of how they were able to decrypt it. And that was one of the main issues with this machine, is that there were 6 unused for this one, and it was a lot easier for them to be able to decrypt this entire message that they sent out. One of the things would be they would have Hitler's name inside of it. Instead of encrypting that, it would just say Hitler inside of it. And is this part of a randomized algorithm? Of course it is, because it's encryption. This is a very extensive encryption right here that they're currently using for it, and it's very difficult to go ahead and process everything for this. For it to not be considered a randomized algorithm, I'm not too sure what would be considered randomized at this point if this was not considered randomized. There is a way to decrypt it, but there's a way to decrypt anything for encryption. So if you guys want to read more about the Enigma machine, go ahead and ask. I'll go ahead and explain as best as I can if you guys want more explanation for it. And if you guys want to read the paper, just go ahead and ask inside the discussion board. I'm more than happy to link it. So another one that I mentioned was a random map generation for games. So this one right here, of course, everybody has heard Minecraft or have played it. So basically for Minecraft, when you generate a map, you're given a random seed. In this random seed, it can take whichever one that you currently, or it can give you any random biome. The biomes are fixed. You have 4 different biomes. You have the desert, you have the forest, and you have the swamp, and then you have just a regular plain field, I believe. So for each of these biomes, whenever you start it up, it will always give you one of those 4 biomes. Basically, with a randomized algorithm, you're giving it a random input for a seed, and whatever it does with it in the middle of the process of it and then spits out at the end, you're going to get an output that is related to whatever you're doing, just like a randomized algorithm. You're giving it a random input, it does stuff in the middle, and then it gives you an optimized output, or the output that you're expecting it to do. And that's what's happening with Minecraft. So for actually a good example would be for speedrunners. A lot of speedrunners in this game is the objective is just to beat it as fast as possible for any speedrunning game, as many people have done it before. And for this one, you want to get a desert biome because it's easy to farm these things called Endermen inside of it to get the eyes. So rambling on stuff, but basically the whole point is to get that specific biome, but you have to reset each time you don't get that biome because it's a random generated seed, so you don't know when you're going to get it. It's generated at randomly, and that's the whole point of randomized algorithms. Everything is generated at randomly, but you're always going to get a specific input or output for it. You always know which one it is. Another one is Stardew Valley. This one I looked up and didn't really understand it that much until I read more of it, and it's basically dealing with the cave systems inside of it, how they generate randomly and increasing vast in size. So with all the caves, you already know that they're going to be caves inside of it, but how far they go is generated randomly, and it's all dependent on the seed that you currently have. Some people may have smaller ones, smaller cave systems, and some people may have bigger ones. It just depends on the seed size. It's all predetermined, but what it does in the very beginning is how it gets there in the end. So that's why randomization algorithms take advantage specifically in game apps, specifically these two. There's a lot more that have been covered for it, but these are the most notable ones specifically for this. And then lastly is searching algorithms. So we have, of course, quicksort, and then we also have the Robin-Karp algorithm, which has already been explained in this video. So with searching algorithms, we have different things that we need to look out for and how they are presented. Some questions to ask is, are they using some sort of hashing? Are they using picking points or at random to find a specific number? How are the inputs decided, etc. There's a lot of things to think about. But for quicksort, when you're given quicksort itself, you're using the random function for testing different cases. Let's say if you generate random numbers itself, put it into an array, sort the array, you're already doing a random algorithm because you're using the rand function itself. There is a predetermined algorithm to use it, but to make it more random, you can actually select different points for the pivot. So instead of using 31 for the pivot, you can use 14, you can use 44. You can start from any of these points and continue the algorithm for wherever point you left off and have it do whatever it would like to basically fix the array to make it inside descending or increasing order. And that's one way to go ahead and take advantage of randomized algorithms, is to go ahead and do it that way, is to pick a random point within a search algorithm and start from there, and then work your way from where the algorithm should be and output it optimally. For the Robin-Karp algorithm, we basically have it, another group had explained it, where we're using the hash function. And with the hash function, you're taking a set amount of characters. Let's say it's 4 or 3 in this case, because you have AAC, which gives you 1 plus 1 plus 2, which is equal to 4. That's the hash function plus the hash code. The hash code is what matters, because now what you're able to do is go ahead and compare the hash code to whatever it is you're searching for. So instead of searching for a string, you're now searching for a number that matches that specific number. Now once you do that, it's a lot easier to find specific things, because it helps the search function. Instead of looking for a set characters, you're not looking for just a specific string inside of it. With that specific string, you're able to find it a lot more optimally. You're able to reduce the search time itself. So with Robin-Karp, one of the main uses for it is actually plagiarism. So let's say if someone uses it for, a good example would probably be for a speech. If someone ended up doing a query on your speech and put in, let's say, obscure word that no one has heard about, and it pops up inside other people's speeches, then of course you would be fined for plagiarism. But that is one of the main uses, is actually for plagiarism or for just word searching in general. When you go into a website and then you go ahead and click on Control F, type in the word that you want, it's creating a hash function for that, so that we can go ahead and store the hash code, and then it's going through each of those words on the page itself to find the specific hash code for it, so that way it can go ahead and highlight it for you and tell you where to go. So those are basically the 3 different forms of it. There is one more form, or one more thing that it does help out with, and it's for load servers. Load servers are a bit more complicated. If you want to know more about load servers, just go ahead and leave a comment at the discussion board. We'll be more than happy to answer more about load servers. It's a little bit more complicated with how they're used. Basically, it's very dependent on randomly asking which server is best to put it into, how much it needs to go ahead and process the time for it. There's a lot of dependent variables for it. So if you guys want to know more about load servers, go ahead and leave a comment. If you guys have any questions or comments that you guys felt like we didn't answer, go ahead and leave them inside the discussion board too, so we can go ahead and answer them to our best of our abilities. Here are our references for the presentation, and thank you guys for watching our presentation. Have a good day.